In this last video, I want to summarize some of the key ideas that we talked about and also look at a quick demo. So, what is logistic regression? Well, our goal with logistic regression is to predict a binary categorical variable, so either a 1 or a 0, as a linear function of features passed through this nonlinear logistic function. And we are modeling the probability that our observation belongs to class 1. The way we came up with this model was by assuming that the log of the odds of the probability of belonging to class 1 was linear. And we sort of reverse engineered that relationship to get this expression for the probability that y is 1 given x. Now, to determine optimal model parameters, we looked at two possible loss functions. We looked at squared loss and cross-entropy loss. Now, squared loss works, but it has its pitfalls. It's not convex, it doesn't penalize wrong predictions strongly enough, and it's also just not that well suited for modeling probabilities. And these are all pitfalls that cross-entropy loss solves. It is convex, it does penalize bad predictions more strongly, and it's better suited for modeling probabilities. And by better suited, I mean that it maximizes the likelihood of observing our training data over all possible model parameters. And that was the subject of that last video. So, you may be wondering, how have we gone through this entire lecture and we haven't actually talked about classification? You may remember our goal at the beginning was to predict categorical variables, 1s and 0s, and all we've done so far is predict probabilities. Well, unfortunately, that's going to have to wait until the next lecture. But what I want you to do is start thinking about how we can use the probabilities that our logistic regression model creates in order to make classifications. Let's sneak in a quick last-minute demo here. So, what I will first do is determine the value of theta hat that minimizes mean cross-entropy loss on my NBA dataset from earlier in the lecture. What I will then do is create this predict probabilities function, which will take in a matrix or list X and a value of theta, and give me the predicted probabilities for belonging to class 1 for these values of X. And so it's really just multiplying X and theta and passing that through the logistic function. But you can see here, when I call this predict probabilities function on my list of X values and the optimal theta hat as determined by scipy.optimize.minimize, I get these probabilities. I wanted to take this opportunity to introduce scikit-learn's logistic regression package. Now, we will talk far more about this in the following lecture, but I think it's useful to talk a little bit about it right now. So, just as we used scikit's linear model linear regression or ridge regression to create those models, all we need to do here is say scikit-learn.linear-model.logistic regression, and we're good to go. There are a couple optional parameters that I'm fitting here in order to sort of match the NBA model that we've been working with. Firstly, I'm going to say fit intercept is false. As we know by now, by default, scikit-learn always provides us with an intercept term in our models, but our model so far has just been theta times our field goal percentage difference, and so we don't want an intercept term right now. By default, there is regularization built into scikit-learn's logistic regression. Now, this is probably a good idea for reasons we will see in the next lecture, but we haven't really covered logistic regression with regularization, so I'm going to set that to none. Lastly, logistic regression sort of throws you a warning if you don't specify a solver. Now, a solver is just the numerical routine that you're going to use to determine optimal model parameters. LBFGS is just one type of them, similar to gradient descent, but it's far more sophisticated than that. And so, what I'm now doing is creating my logistic regression model object, and I will fit it the same way I've fit my linear regression objects before. I will pass in, the field goal percentage differences as my X, 1 column as my Ys. And so After doing this, I can look at the coefficient of my model, and you will see that it's the same value that we manually determined by calling scipy.optimize.minimize on the mean cross entropy loss for the NBA dataset. You can see that they're basically the same. They agree to the first two decimal places, and then after that, there's some numerical precision issues that prevent these from being exactly equal. But you can see that they're generally the same thing. Scikit-learn has a built-in predict probability method that can sort of replicate the behavior of our manually created predict probabilities function. And so if I call model.predictproba on 0.1, what this will tell me is the predicted probabilities of this observation belonging to class 0 and to class 1. So what this is telling me is if my field goal percentage difference is 0.1, there's a 95.5% chance of belonging to class 1 and a 4.5% chance of belonging to class 0. What we really care about is the first element of this array, because we are interested in modeling the probability of belonging to class 1. And so what I can do is call this on my entire set of field goal percentage differences and then look at just the first column of these. And you can see that the values that we get are the exact same as the ones we got with our manually created predict probabilities method. And so the reason I'm showing you all this is because hopefully it demystifies the logistic regression package in scikit-learn. It may seem like it's doing something magical, but it's really not. We know the function that it's minimizing to come up with these predictions. Now I want to give you a sneak peek preview of what we're going to do in the next lecture. Not only does scikit-learn have a predict proba method built in, but it also has a predict method built in. Okay, just as linear regression had a built-in predict method. When I call it, it doesn't give me probabilities, but instead gives me ones and zeros. So what I want you to think about is how did scikit-learn go from these probabilities to these zeros and ones? And that will be the topic of the next lecture. More specifically, in the next lecture, we will talk more about how to go from probabilities to classifications, and we will talk in great detail how to evaluate the quality of a classifier now that we will actually be able to make classifications. But that's it for this lecture.